Good morning, everyone. Thank you all for coming to my talk today. My name is Boris Kolpakov, and I'm a founder and a software designer at Code Synthesis, a company focused on the development of open source tools and libraries for C++. The topic of today's presentation is ODB, an object relational mapping system for C++. I'm sure most of you are familiar with the concept of object relational mapping, but just to recap, the basic idea is to be able to persist C++ objects in a relational database without having to deal with tables, columns, or SQL. Now, when it comes to ORMs, different levels of functionality can be implied by this term. So it's useful to discuss what ODB is and isn't. Let's first start with what ODB won't do for you, but also won't ask you to do. There's no manual parameter binding or result set extraction in ODB. All the other C++ mappers out there require you to write some custom conversion code or call some macro for every persistent class and every persistent data member inside those classes. This is a maintenance nightmare. Sorry, actually that's for a second point. So that was about no writing of mapping and registration code. ODB doesn't require you to do manual parameter binding or results set extraction. Those of you who had a privilege of accessing an SQL database using a low-level C API, I'm sure can attest that it makes for some really tedious code. ORMs also sometimes get a bad rap for having an innocently looking operation result in hundreds or even thousands of database statement executions under the hood. As a result, with ODB, we've decided to stick to the one database operation translates to one statement execution principle as much as possible, and where not possible, clearly warn about the implications. Finally, if you are looking for a framework, you've come to the wrong place. ODB doesn't dictate how you should write your application. Instead, it's designed to fit into your style and architecture by only handling object persistence and then getting out of your way. In particular, there's no special base class from which you have to derive all your persistent classes, nor are you required to use special containers or smart pointers. Okay, let's now take a look at what ODB can do for you. ODB will automatically generate database conversion code from your class declarations, and it's capable of doing that for any standard C++. You might be wondering how, and I'll answer this question in a few slides. ODB also provides object-oriented, multi-threaded database access API with encapsulated connection management. Then there's the statically typed C++ integrated query language, which we'll examine in detail later in the talk. Because the database conversion code is automatically generated, it's easy to switch from one database vendor to another. So we got database portability. In my BooSCon 2011 presentation, I also gave a presentation on ODB. I don't think I was even on a third slide when someone from the audience asked, but what about schema evolution? And that was a good question, because most of our applications will have to evolve with time, but still be able to access databases created by earlier versions. In 2011, all I could say, yeah, it's a hard problem, we are thinking about it. Today, I'm happy to say that we have a solution. So we'll examine that towards the end of the talk. Finally, ODB is very flexible and customizable. It can either completely hide the relational nature of the underlying database or expose some of the details as required. At an extreme, ODB can be used as just a convenient way to extract data from query results. Currently, ODB supports MySQL, SQLite, Postgres, Oracle, and Microsoft SQL Server. With ODB, you can also use multiple databases from the same application. The multi-database support comes in two flavors, static and dynamic. With static support, we use the concrete database interface for each database. With the dynamic flavor, we use the common interface, and most of the application code need not be aware which database it's actually working with. One nice feature of this static and dynamic support is that you can always drop from the dynamic to static support if you need some database-specific functionality. Okay, ODB supports C++98 with optional support for some components from technical report, from the first technical report. Things like new containers and smart pointers. ODB also supports C++11, and by this, I don't mean that we just made sure everything compiles in this mode. Rather, ODB takes full advantage of new language features. Specifically, R-value references are used throughout the runtime and the generated code to minimize copying. Then, as we will see in a moment, range-based for is really handy for query result iteration. Where ODB exposes a callback mechanism, for example, a prepared query factory or a data migration function, then we can use lambdas. Finally, ODB integrates with the new components from the standard library so that we can seamlessly use smart pointers and new containers in our persistent classes. I'll use a lot of C++11 in examples in this talk. Yes, question?
Is it still possible to use it with a 98 compiler?
Yes.
Okay.
Yeah. Oh, sorry, need to repeat the question. Is it still possible to use ODB with C++98? Yes. Yeah. We will still have to support both standards still for probably many years to come. Okay, so how can ODB automatically generate database conversion code for any standard C++, 98 or 11? There's no magic here, and we didn't implement our own compiler. Underneath, ODB is implemented as a GCC plugin. Advantages of using GCC is maturity, portability, and one of the most complete C++ implementations, C++11 implementations out there. Now, some of you may think, well, if ODB is using GCC underneath, then that also means that my application has to be built with GCC. This is not the case. ODB is implemented in standard C++, and the generated code is standard C++. So the output of ODB compiler is actually plain standard C++. So we can use any reasonably modern C++ compiler to build the runtimes in our generated code. In particular, we test every ODB release on these platforms and with these compilers. We also provide a pre-built binary of the ODB compiler with a private copy of GCC hidden inside for all of these platforms. So as you can see, things are quite portable. In particular, if you see that the project builds with Sun Studio, then you can probably build it with your toaster. Who knows what that is?
That's a Raspberry Pi.
That's right. So that's a Raspberry Pi ARM computer that costs $32. And ODB runs on that too. ODB and SQLite turned out to be quite a popular combination for mobile and embedded projects. Just to give you an idea of the footprint that we are looking at here, a statically linked Hello World application, which actually also uses queries and things like that, built for Raspberry Pi, is about 500 kilobytes. And that includes the ODB runtime and SQLite, which itself is over 400 kilobytes. We have a guide for cross-compiling ODB for Raspberry Pi and now also for Android. Let me also mention a few performance numbers. ODB was designed from ground up with high performance and low overhead in mind. In particular, it uses prepared statements throughout and caches, connections, statements, and even memory buffers. When it comes to the database access, ODB uses low-level native C APIs to minimize overhead and gain access to all the available functionality. Finally, ODB imposes 0 per object overhead. There are no hidden special data members in your objects or special base classes. So the size of your persistent class is basically what data members you put in it. Here's some indicative performance numbers for loading an object with about half a dozen members, strings, and integers. In particular, SQLite, being an in-process database, is really fast.
What platform did you run that on?
That was on, I think it was on a Xeon, 2 generations old Xeon. So it's a pretty beefy machine, but yeah. Okay, I think not talk about an open source project will be complete without mentioning the license. ODB is dual licensed under the GPL and a commercial license. In particular, that means that if you are using an ODB-based application within your organization, for example, by running it on your company's servers, then you don't need to worry about any of the GPL restrictions. We also realize that neither of these two options are particularly suitable for other open source projects which use a more liberal than the GPL license. As a result, we've decided we'll just grant a licensing exception to any open source project that is interested in using ODB. In fact, we already granted one to a project. You can read more about all these options on the ODB licensing page. Okay, enough talking. Slide number 12. Let's see some code, shall we? So we are writing a simple bug tracker, and the first version of our bug report has just 4 fields. It's the bug ID, the bug status, which can be open, confirmed, or closed, a short summary, and a full description. Let's not see what it takes to convert this class to an ODB persistent object. The first change that we make is add the object pragma. This pragma tells the ODB compiler that this class is persistent, so it needs to generate conversion code for it. The next change is the friend declaration. All our data members, as you can see, are private. And this declaration allows the ODB-generated code to access this data. Now, if all our data members are accessible through public accesses and modifiers, then we don't need this declaration. ODB will automatically discover and use these accesses and modifiers to get hold of the data. The third change is the addition of the default constructor. While not strictly necessary, it makes working with persistent objects easier. As you can see, we can also make it private. Finally, we mark the bug ID as an automatically assigned object identifier. While in ODB it's possible not to have a class without an object ID, normally most persistent classes will have an object ID. Okay, so those are the changes we had to make. As you can see, we don't need to do anything special for every persistent data member. So if you add another data member, recompile everything, it works. No changes required. Now, some of you may not like this idea of peppering your beautifully crafted classes with these pesky pragmas. Good news is you don't have to. The mapping can be provided completely out of class and even factored into a separate header file. In fact, if all our data members are accessible through public accesses and modifiers, and we have a default constructor or are willing to live without one, then the mapping can be completely non-intrusive. So you can adapt your persistent class without actually making any changes to it. Okay, let's now take a look how the the build workflow of our application changed. Oh, sorry, question. Yes.
Can you go back to the previous slide?
Yes.
What about the friend class declaration?
Okay, repeat the question. What about the friend class declaration? That's why I said if you have public accesses and modifiers for all your data members, then you don't need the friend declaration. ODB will automatically discover those accesses and modifiers and use them instead of getting to the members directly. Does it make sense?
So it'll look for a set and a get.
Yeah, exactly. And supports all the, it automatically discovers all the common, set and set, get capital name, get underscore name, things like that. And if you use a less conventional way, you can always explicitly specify which accessor to use. Yes, question?
So if you only have private member variables, do you have to put the friend class inside of the class declaration, or can it be outside and it's separate header class?
So the question is, if you have all your data members are private, can you put the friend declaration outside of the class? And the answer is no, standard doesn't allow that. That would be illegal C++. Yes, question?
The ID member, is that exclusively for use for the ODB and filled in by the ODB?
Let's go take a look at this one. So the question was, is the ID is exclusively for use by ODB? That's actually a good question. The idea is that your object has the notion of identity. And usually it corresponds to something natural in the object state. Like, just to give you an idea, let's say you're creating, I don't know, a person class, persistent object. Then natural things that would be IDs, for example, can be an email, because it's unique, well, more or less. Or you can use some government-issued ID like Social Security or passport number. So things like that. In our case, normally when you go to Bugzilla or whatever, there's always be an identifier, a number for a bug by which it is identified. So here we kind of naturally mapped this bug ID to the object ID. But we'll see where this ID is actually useful, where you use it when working with persistent objects.
So would it be a key?
Yes. Yeah, if you know a bit about the relational databases, an object ID is mapped to a primary key. Okay, everyone's good. And here we marked our ID auto assigned, which means that we don't have to provide the ID ourselves. The database will generate one for us. So it's like an auto increment primary key. Okay. Okay, back to the workflow, build workflow. So once we start, here's a typical simple C++ application. We have a header file and a source file, which includes the header file. And the source file is compiled with some C++ compiler to an executable. Once we start using ODB, some headers are compiled with the ODB compiler. The output of the ODB compiler is a set of C++ source and header files. You can also ask the ODB compiler to generate the database schema for us for our persistent classes. The application source code includes the generated header file in order to gain access to the database conversion code. Finally, we compile the generated source code along with the application source code with a C++ compiler of our choice. So while it kind of complicates the things, but looks a bit, it's actually fairly straightforward. Okay, everyone's good? Let's now take a look at how we can invoke the ODB compiler. Here we assume that our bug class is saved to the bug header file. As I mentioned earlier, ODB compiler is a real C++ compiler. Underneath it's basically GCC. So we can use common options such as -I or -D when using the ODB compiler. For example, we can tell the ODB compiler where is our boost. Here there's a. The next example shows how we can turn on the C++11 mode. Here we also make the default object pointer the standard shared pointer. With this change, the generated code will now always return persistent objects as shared pointers. Generally a good idea. The last example shows how we can request the generation of the database schema for our classes. And that's what it will look like for our bug report and the Postgres database. As you can see, the ID is mapped to the primary key, as we just talked about. And in Postgres, big serial is basically an alias for auto increment. Okay, so we have our persistent classes and we generate the database conversion code. What else do we need to be able to to file our first bug report? The last thing that we need is the database instance. This example shows how we can create one for the Postgres database. And this example is for SQLite. With ODB, we can also pass the database as a common interface in order to keep our application code vendor neutral, so that we can switch between databases with a simple recompile. Okay, now we're all set to file our first bug report. First thing that we do is create the instance. Then we start the transaction. As a general rule, every database operation is performed within a transaction. After that, we call the persist function, which returns the ID, the automatically assigned ID of the newly persisted object. Finally, we commit the transaction to make the changes permanent in the database. Now, sometimes you may want to see what actual database statements are executed as a result of your calls. This, for example, can be useful if performance doesn't match your expectations. ODB allows us to specify a statement tracer on the connection, database, or transaction levels. For example, if we enable statement tracing for this transaction, then we will see this SQL insert statement executed underneath. Question? Yes?
A question about the database connection. So if I connect to a database and the tables do not exist yet, does ODB auto-create them with a schema, or do I have to do that in a separate process?
So the question was, when, say we run this transaction and the schema doesn't exist in the database, will ODB automatically create it, or do I have to create it ourselves? And the answer is, it won't automatically create it in the sense that, okay, there's no schema, let me create one, but there are various options for you to basically automatically create, just more explicit. But I'm going to talk about database schema in more detail later. So I think you will kind of see how it's done. There will even be a piece of code that shows how to do that. So here we assume that the database schema has been created already in the database, and we'll talk more about how this can be done in a moment. Okay, any other questions? Okay, let's say we want to load the bug report given its ID. This is an example of where, how you use ID most of the time. That's basically the identifier of an object in a database. Normally, you don't want to store the object all the time in memory, in the application memory. So you'll store an ID, and when you actually need it, you load it using this ID. So if we, as I mentioned earlier, in ODB, you don't have to have an ID. But in this case, you cannot use load, for example, because there's no ID. So you will have to use a query facility, about which we'll talk in a moment. Okay, so we have an ID and we want to load the bug report. This transaction shows how we can do that. We can also load the database state directly into an existing instance, as shown in this example. Remember I told you that the default constructor is useful but is not strictly necessary. Well, if we don't have one, then that's how we'll have to load our objects. You'll basically have to construct the object in some ad hoc way ourselves. For those interested, there is the select statement that is executed as a result of this, of one of these calls. Okay, pretty simple, I think. The other common database operation is updating the state of an object in the database. Here, for example, we may want to change the status of our bug report to confirmed. This transaction shows how we can do that. Again, we load the bug, change the state, and update it. And it's the update statement. Okay, let's now see how we can, question, sorry.
So it's always a complete update because there's no detection of which member changed. Because that could be costly with big objects.
Okay, the question was, so it's always complete update of all the data members even though we only changed one member. And that's actually a really tricky question to answer. The answer is yes, currently. And it's also yes to the fact that that might not be optimal. But the kind of the trade-offs that we are evaluating here is whether to create the update statement dynamically or have it, compile time generated, prepared, sitting in memory, ready to fire. So you see, if we update just one member, then we cannot kind of pre-compile the query. We have to construct it, execute it, which can be much more expensive. So I don't know, we don't want to go that route. A lot of other ORMs, especially for other languages like Java, they do a lot of dynamic query composition at runtime. We do everything statically. If you look at the generated C++ code, you'll actually see the strings of complete queries inside and update statements, things like that. So what we are thinking of doing is we will allow, that is still not implemented, kind of in the design phase. We will allow you to segment your data members in a class into sections. And then you can update different sections individually. Okay, makes sense? Cool. Yeah, and that same mechanism will also allow you to lazy load different sections, depending on what you need. But yeah, I'll talk about that later. Okay. Let's see how we can query the database for all open bug reports. The first two lines in this example define the query and result types. The highlighted line is where we actually perform the query. The query type has members corresponding to, such as status, corresponding to data members in the persistent class. We can use these members to create a query condition. As you can see here, we just use this data member and say that it must be open. That's our query condition. Now this is an example of what we call a C++ integrated query. The idea is basically we created a little embedded DSL language, domain-specific language, which mimics what you would write in C++ rather than SQL. But underneath, it is translated into SQL. The result of the query is a container-like object which supports forward iteration. So it conforms to the standard forward iteration concept. There you can see the loop. A C++ 98 style loop. Doesn't look, kind of easy to understand, but not particularly pretty, right? Let's now take a look what a C++ 11 version would be. a range-based for loops surely makes things tidy. And notice also that we don't need the result type def anymore. We just use the query directly in the for loop. Yeah, I think that is really cool. For those interested, yes. Sorry.
Like no bugs are open.
Sorry?
Now you're invoking the query now inside of the for loop. How do you know outside of the for loop if the query was empty?
Well, you'll get an empty result object, and there will be no. Sorry, I repeat the question. How do we, if there are no open bug reports and the result of a query is empty, how can we use it in a for loop? And the answer is, I mean, you can iterate over an empty vector, right? You just won't have any iterations. So exactly the same principle. The result object, which is a container-like object, will be empty. So you'll just, these 3 dots, they will never get executed.
That's not what I meant.
No? Sorry. Okay. Can you try?
You simply would have in that case to look if, I guess you have, if you're returning a vector, you can test on the size if you need to know if you have objects or not.
Okay, so the comment was that in case of a vector, we can always check if it's empty. And the answer is that there's an empty function on this result object which you can call and check as well. It is like a standard container, not exactly, but yeah.
Or you use a Boolean flag in the loop body. Something like
Yeah.
bool found is false and inside the body true, then no.
Mm. But yeah, you can call empty. There is empty function which tells you whether the result is empty or not. But yeah, I think I see your point. You're basically saying that if we need to check whether the result is empty, then we will have to first create the result variable, check whether it's empty, and then if it's not, then we iterate over loop. Fair enough. Okay, that's the select statement that is executed for this query. Let's now take a look at some more interesting examples of queries. As the first 2 lines show, you can combine multiple query conditions with logical operators. Again, very C++-like, nothing like SQL. The next block shows support for by reference parameter bindings. By default, parameters are bound by value, but we can also bind them by reference. This is particularly useful if you want to execute the same query multiple times. The next line shows support for native queries. So we just saw language integrated queries, but there's also support for native queries. The idea is here basically that you can create a completely custom where clause for your select statement with support for parameter binding. So you still can bind parameters by value or by reference. Here you have to specify binding explicitly. The last line shows dangers of native queries and also highlights the advantages of C++ integrated ones. Because in native queries we use strings to identify columns and the expressions are typeless, it's easy to misspell things, and such errors will only be detected, if at all, at runtime during query execution time. So there are dangers. If we want to execute the same query multiple times, then it's a good idea to prepare it for performance reasons. This example shows how we can do that. First we create the query condition, exactly the same code. Here we use by reference parameters so that we can query for different states of our bugs, for different statuses. Then we actually prepare the query. And once this is done, we can initialize by reference parameters and execute the query as many times as we want. And that will be as efficient as it gets. Yes, question?
The string bug query, so the all prepared statements are named, or?
So the question was, here we pass what looks like a name, and our all prepared queries are named. Again, nice question like that. The answer is yes, and there are two reasons for that. First reason is that some databases like Postgres, they require you to name prepared queries, and we didn't want to go into this whole problem of automatically generating names in a thread safe. And so, and the second, well, that was kind of one reason, but there's actually a second reason which makes the first point moot. The second reason is that this is a simple example, but you can also cache prepared queries on the connections and then look them up. And when you look them up, you use this query name. So it kind of fitted nicely together. And we also try to be as lightweight as possible. So the name of the query is actually, it should be a static C string. It cannot go away until the prepared query is gone. So because the mechanism is kind of designed to achieve the most efficiency, we just eliminated all the overheads possible. And that's how you will normally use it, anyway.
So if I pass local standard string cster, it would later crash?
Well, in this example, no. If for example, you created a string here and then you passed it there, then
Pass the standard string whose lifetime was shorter than the query. I pass it using C string and then it would crash.
Okay, so I'll repeat the question. So if we use a standard string and we pass an automatic, a local standard string, and we pass its underlying string as a name of a query, and then the lifetime of this string is shorter than the lifetime of the prepared query, then yeah, it will undefined behavior, I would say. Yeah. But yeah, crash basically. Okay, everything's good. Okay, the last operation that we haven't talked about is deleting the state of deleting persistent objects from the database. We can do it by either passing the bug ID. Again, that's where you use ID. As you can see, ID works as a proxy for the object in many cases. Or we can pass the object itself, or we can use a query condition to delete multiple objects from the database. For example, we can delete all the closed bugs from our database. That's the delete statement that is executed for the first two options. I think pretty clear everything, right? Okay, that's pretty much it for the basics. I mean, we've covered all the basic operations that you need to know to get started. And now we'll move to some more interesting things. Right now, our bug report is very bare bones, very basic. The first thing that we would like to do is to add the creation and modification dates. So the question is, what can we use to store these timestamps? Well, the Boost datetime library sounds like a good idea, right? So we can add the data members, but the question is, will it just work? And the answer is, yes, it pretty much will. We just need to take a quick detour and talk about ODB profiles. An ODB profile is a generic mechanism for integrating ODB with widely used frameworks and libraries. A profile is a glue code which allows us to use containers, smart pointers, value types from these frameworks and libraries as if they were natively supported by ODB, like standard string, for example. Currently, ODB provides profiles for Boost and Qt, but it's easy to write a profile for your own library if you want to. To enable a profile, we use the -p ODB compiler option. When it comes to value types, the Boost profile covers the unique identifier and datetime libraries. We can also use the optional container, the Boost optional container, to handle null columns. So going back to our bug class, all we need to do to be able to use Boost datetime library is to just enable the Boost profile. I don't know if anyone here is interested in Qt. Nobody? Okay, cool. So there's also the Qt profile, which has pretty similar coverage, basic types, string, unique identifier, and byte array, as well as the datetime types. And that would be the Qt version of our bug report using Qt types. And again, that will just work if you pass the -p Qt ODB compiler option. Okay, so that all clear, right? Nothing surprising. So far we've only used simple types such as integers and strings as data members in our persistent objects. But sooner or later, probably sooner than later, rather than later, we will run into a situation where we want to persist something more interesting, like a container. ODB provides built-in support for most standard containers, things like vector, list, map, set, as well as C++11 array and unordered containers. The Boost profile provides support for the mighty multi-index container. I don't know if anyone of you used that container. At first it gets a bit difficult to start, but it's quite great. Similar, the Qt profile covers pretty much all the Qt containers. It's also fairly easy to support custom containers. As you will see, it's kind of recurring theme in ODB is that whatever we do, whatever built-in support we have, you can also implement support for your own things using exactly the same mechanism and with exactly the same integration. Okay, as an example, let's extend our bug report by adding a vector of comments and a set of tags. As you can see, we just add those data members and it just works, nothing special to do. This is the Qt version again. Here we use the QList, QHash. Well, I said it just works, but actually there's a small catch. See, ODB doesn't know whether what modifications were made to the container, if any. So an update operation on an object that includes a container can be rather inefficient. To see why, consider a transaction that adds a comment to an existing bug report. Let's also assume that this bug already contains 20 comments. If we enable statement tracing, we'll see a surprisingly large number of database statements executed for this simple transaction. The problem is ODB cannot distinguish between a simple append and a complete container override. The standard vector just doesn't include this information. So ODB has to assume the worst case and transfer the complete container state to the database. So that's why you will see 23 database statements for something simple like that. Clearly not a good thing. ODB removes this overhead with the help of change tracking containers, which basically ODB provides change tracking equivalents for some of the containers I mentioned earlier. A change tracking container, in addition to containing its elements just like an ordinary container, also includes change state for each element. Using this change state, ODB can then execute the minimum set of database operations necessary to synchronize the container state with the database. So in our example, if we used a change tracking container, ODB will know that it's a simple append to the end and it'll just execute a single insert instead of 22, one delete and 22 inserts. So this can be a major performance improvement. Currently ODB, normally a change tracking container can be used just like as a drop-in replacement for the ordinary one with a few interface differences, mostly when you modify the container. Currently ODB provides change tracking equivalents for standard vector and Qt list, and both impose 2 bits per element over here to store change information. Okay, so we've seen how to use simple data members and containers in our persistent classes. The other kind of more complex data type that we might want to use is a composite or multi-column value type. In ODB, these types have to be explicitly marked with a value pragma because there's actually a code generated for them. Composite values can use simple values, other composite values, containers, and objects to pointers to objects. We'll talk about pointers to objects later. We can also derive composite values from each other, and there's support for multiple inheritance if you want that. We can also use composite values in object IDs, in which case you will get a composite primary key. As an example, we can extend our comments by adding the creation timestamp. Also, I think pretty straightforward. Here we mark it as a composite value type. Okay. The last kind of data member that we haven't covered is a pointer to object. Pointers to objects are used to represent object relationships. ODB provides built-in support for raw pointers, standard and unique pointers, as well as shared and weak pointers from the C++11 and TR1. The Boost and Qt profiles provide support for their versions of weak and shared pointers. Again, it's also fairly easy to add support for custom smart pointer. You just provide a thread specialization, that's it. Okay, one pretty big omission in our bug report is who actually reported it. So let's fix that, and by adding a user persistent object, this is all fairly straightforward, nothing that we haven't seen. As you can see, just a side note, here we use a non-automatically assigned ID. We use an email to identify a user, like for example, Bugzilla does that. That's what you use to log in. Okay, once this is done, we can add a pointer to the user object and call it a reporter. This is an example of a unidirectional to-one relationship. That is, a bug can be reported by a single user. Now, it can also be handy to know which bugs a particular user reported. A vector of pointers will do the trick here. This is an example of bidirectional many-to-one relationship. Now, if you look into the schema generated for this relationship, you will notice that the bug table contains a column corresponding to the reporter pointer, and we also have a table corresponding to reported bugs container. Now, if you are a relational modeling expert, you will immediately say, no, that's redundant. See, the thing is, in relational databases, a reference can always be traversed in both directions, unlike C++. So to fix this, we can tell the ODB compiler that this side, or one of the sides of this bidirectional relationship is actually a mirror or inverse side of the other. Once we do that, the reported bugs table will be gone, and we can again tell everyone that our schema was designed by a relational modeling expert. Okay, here's the final version of our bidirectional relationship. We have a problem here. Can anyone has any ideas? Sorry?
Sacred dependency.
Circular. So yes, the answer from the audience was we have a circular dependency. So we basically have, well, an ownership cycle as it is normally called. So we have a user class which owns a bug class and a bug class that owns a user class. That's right. Well, that's actually only one of the problems. We have two problems. As you correctly pointed out, first is the ownership cycle, and it's fairly easy to fix, just weak pointers to the rescue. The second problem is a little bit more interesting. Let's say we loaded a bug report and we want to print some basic information about it, things like a summary and who reported it. When we load the bug report, the bug object, we also then it references its reporter. So that object has to be loaded as well. But then, in turn, the reporter has a whole list of other bugs that it reported. So those have to be loaded as well. As a result, an innocently looking transaction with a single load call can pull hundreds of objects from the database. Clearly not good. That's actually the remember I told you we try to do the one database operation, one database statement execution mapping as much as possible. This is a good example where it's kind of expected behavior and you can end up with hundreds of statements executed. So in the manual we clearly identify this issue. So the ODB answer to this problem is lazy pointers. Lazy pointers provide finer grained control over relationship loading. For all the smart pointers I mentioned earlier, ODB provides lazy versions. Here's an example of how we can fix our problem, our relationship, using lazy weak pointer equivalent for the standard weak pointer. The lazy weak version, in addition to the interface exposed by the weak pointer, adds a couple of extra functions such as load, which we can use to load the pointed to object when and if necessary. So going back to our example, when we load our bug report, it will only load the user object, but because these pointers are lazy, they won't be loaded. Though if we need to, we can go and load them explicitly. Okay. And that's the cute version of the same relationship. Cool. Okay, let's say we want to print a short report of all the open bugs in our database. I'll print the bug ID, summary, and who reported it, one bug per line. While this transaction works just fine, its performance can be improved. Let's first see why, and then we'll talk about how. There are two things that contribute to the inefficiency of this transaction. Firstly, we load all the data members for both bug and user objects, even though we are only interested in a small subset of them. Secondly, for every bug that we load, we execute a separate database statement in order to load its reporter. It would have been more efficient to do it in a single statement by joining the two tables together. Well, if you know how the relational database works underneath. The ODB answer to this problem is views. An ODB view is a lightweight, read-only projection of one or more persistent objects, database tables, or it can be a result of a native query execution. ODB views can be used to load a subset of data members from any number of objects, execute and handle a native query, including aggregate queries, as well as join multiple objects using either custom join conditions or relationships between them. Also note that ODB views and database views are different things. In particular, ODB views are not mapped to relational database views. So let's now see how we can create a view that will allow us to only pull the data members that we actually need, and also do that in a single statement. So that's all that we need to do. So the view header lists the objects on which this view is based. ODB compiler will automatically figure out how to join their tables based on the relationship between them that we saw earlier. ODB will also figure out which the view data members come from which objects based on their names. So we don't actually need to do anything. Don't have to do much. Let's now see how we can change our transaction to use this view. All we have to do really is query for the view instead of the object. Otherwise, it's pretty much the same. And to prove that we actually achieve what we tried to achieve, here's the SQL select statement that is executed for this transaction. So we just pull what we need, as you can see from different tables, and we do it. We join the two tables together. Okay. Let's say we want to allow a user to change the status of a bug report. That is, we will load the bug report, show the current status, maybe some other fields, and then ask the user to enter the new status, update the object, and save it in the database. So this transaction shows how we can do that. Because we do everything within a single ACID transaction, nobody can change the object while we are waiting for the user input. Similarly, we won't override a new value that might have been written in the meantime. So all seems good so far. There's actually a bad side to this as well. Imagine what happens if a user decides to go grab a coffee while thinking about the bug report, about the new status. During this time, active transaction is holding up database server resources. Even worse, because we have already loaded the object, nobody else can modify it until the transaction is finished. So in this light, our transactions should be short and fast. Doing any kind of user input within a transaction is definitely a bad idea. So how can we fix this? Well, the first thing that comes to mind is to split the transaction into two. I think you can all see what the problem is now with this approach. Because we no longer do everything within a single transaction, anyone can update the object underneath us while we are waiting for the user input. As a result, we will overwrite a new value based on the outdated information. This problem of long-lived application transactions is fairly common in the database world. And the solution that is normally used is optimistic concurrency. In a nutshell, the idea is to hope for the best, but be prepared to handle the worst. Or more specifically, to hope that nobody will change the object while we are working with it, but detect and recover if they do. ODB uses object versioning. Thank you. ODB uses object versioning to implement optimistic concurrency. That is, whenever an object is updated in the database, ODB will increment its version. Also, before the update, ODB will check that the versions as seen by the application and as seen by the database match. If they do, then it means that the object hasn't been changed since it was last loaded into the application's memory. Otherwise, if the versions don't match, then the update fails. Because an application transaction that involves a recovery from a failed update can be significantly more expensive than a successful one, optimistic concurrency works best for medium to low contention levels, where most application transactions succeed without any update conflicts. So let's see how we can use optimistic concurrency to fix our transaction. First thing that we need to do is to declare our object as optimistic. Yeah. I think it's a good name. I like it. It is optimistic. Believes nobody is going to change it. We also need to provide a data member which will store the version. Now, ODB will manage this thing completely. So all you have to do is just to have one. Don't need to worry about it. Once this is done, let's take a look how we can fix our code. We will basically try to fix the first attempt of fixing our stuff, where we split the thing into two transactions. So the first transaction where we actually loaded the object is exactly the same. And the interesting part is the modification. Here, our first attempt is exactly the same as before. We ask the user to enter the new status, and then we try to update it. If that succeeds, then we are done. You know, the object hasn't changed underneath us, all is good. If, however, the object has changed since it was last loaded, then the update will fail. Here, we get this exception. So what we do, we reload the object and repeat the whole sequence. So we show the user the current status and ask him to enter the new one. So that's a fairly common pattern of recovering from a failed update. You basically just kind of retry the whole thing. And because we're optimistic that this won't happen too often, then the performance is normally pretty good. Any questions about this? No? Good, cool. Either make a lot of sense or no sense at all. I don't know which one it is. Okay, sooner or later, we'll run into a need to persist a polymorphic class hierarchy. For example, in our bug database, we might have two kinds of issues.
Just a quick question on that previous slide.
Yes.
Did I understand right, you're committing the reload or the update, depending on whether you throw or not? You have a commit underneath the try-catch block.
Catch block. Yes. Okay. So I think the question is, what happens? You know, how does this whole transaction logic works, right?
Yeah, I just wanted to make sure that the commit was valid for the reload then, so what's happening.
Yeah, it is valid. So what will happen here? We start a transaction. We try update. If it fails, then we reload. The transaction is committed, even though, well, we didn't change anything, so it's a no.
Commit, but it's appropriate.
Yeah. And then we kind of start the loop from the beginning. We start another transaction, try exactly the same thing. Okay. Okay, so again, back to our polymorphic hierarchy. So in our database, for example, we might have two types of issues, bugs proper and feature requests. Some of the data members might be common to both of them, but some may be specific to a certain kind of issue. For example, a bug might need to capture a platform that it affects, while a feature might have the number of people voted for it. Also, when we don't need to distinguish between bugs and features, we would like a convenient way to work with both. I think we can all see what kind of mechanism this calls for, right? A polymorphic class hierarchy. In our case, we could create a common base class, and let's call it an issue, which contains all the common data members. And then we add the derived classes and add the data members that are specific to each kind of issue. Pretty straightforward stuff. Let's now see how we can persist something like this in ODB. ODB uses the so-called table per difference mapping to implement polymorphism. That is the root class of the hierarchy. The table corresponding to the root class of the hierarchy contains all the common data members, while derived tables only contain data members corresponding to derived classes. When it comes to using polymorphic hierarchies with database operations, we can either use the actual derived type or the common base interface. Let's see some examples of that. First thing that we need to do is to declare the object polymorphic, the root of the hierarchy polymorphic.
Can you put something like, I guess, chain the properties, so if you say polymorphic and optimistic?
Yes, it works. Yeah.
Repeat the question.
Oh, sorry. So the question was, can you have like a polymorphic optimistic object? And the answer is yes, you can. It's kind of orthogonal concepts. So we first mark it as polymorphic. The class has to be also polymorphic in the C++ sense. That is, it has to have one or more virtual functions. Having a virtual destructor is generally a good idea. We don't need to do anything special for derived classes. ODB will automatically know that they are polymorphic because they derive from a polymorphic class. Okay, let's now see how we can use these polymorphic classes in database operations and start with a case where we pass one of them to one of the database functions. In this case, we can pass the common base interface, and the ODB compiler will automatically use the actual dynamic type of the object. For example, we can persist, update, or reload either a bug or an issue via the issue common interface. Sorry, a bug or a feature via the issue common interface. Everyone is happy with this? I think kind of. I hope that the whole theme is that it just works. The more interesting case is when we return a polymorphic object from one of the database functions. In this case, we again can specify the base interface, like here in load, and the result will be either a bug or a feature. So ODB will automatically figure out which one it is, and pull all the data members from different tables. I think that's pretty cool. The same applies to a query. The query result will be a mixture of bugs and features. The query case is actually quite interesting in that, depending on which type we specified, we can query for all open issues, query for open bugs, or query for open features. Okay? Kind of fits nicely, I think. Okay, so everyone is happy. Oh, sorry, question.
So the query of the issue, you have the equivalent of a dynamic cast or a type ID from that, so you can determine what it was?
Yes, because that's exactly, sorry, the question was, when the result of a query contains a mixture of bugs and features, can we use a dynamic cast or type ID to figure out which one it is? And the answer is exactly that. You can either do that, use dynamic cast, for example, because remember I said that the root of the hierarchy has to be polymorphic in the C++ sense. That's exactly so that you can actually use dynamic cast on it. But what you can also do is probably better design is to use virtual functions. For example, in our issue, we might declare a virtual print function and implement it differently in bug and feature. And then in this for loop, we just say I pointer print. And that's it. You don't even need to discover which ones it is. Good? It's happy. Okay, let's now talk a bit more about database schema. That's where your question is going to be answered, I hope. By database schema, I mean the SQL statements that create tables and all the other necessary artifacts, such as indices, that are necessary to store our persistent objects. As we've seen before, we can ask the ODB compiler to generate the schema for us. This approach is normally called as object first. The alternative approach which is called database first, assumes that the schema is created first or already exists, and we need to map our classes to this custom schema. When it comes to the generated database schema, we can ask the ODB compiler either to generate a standalone SQL file or embed the schema creation code into our generated C++ code. in the latter case, we can create the schema programmatically from within the application. So to answer your earlier question, you can either run the SQL file out kind of in some specific way. For example, when your application is installed, part of the installation, you create the schema using the database facilities. Or you can detect at the first startup that the schema doesn't exist and create it from within the application. Now the standalone SQL file normally is preferred approach for client-server database like Oracle, for example. In big companies, you won't even be able to run the schema until it's reviewed by the DBA and things like that. So you generate an SQL file, send it to your DBA, he will say, yeah, looks good. And then they run it on a production server. While the embedded schema is most useful for, say, SQLite, where your application manages everything. So, in fact, our DB compiler will generate SQL file by default for all databases except SQLite, and for SQLite it will generate it embedded, which is like the most common use cases for them. Okay, so good, everything's happy. If we use a custom schema, then the ODB compiler allows us to map our classes to specific tables, data members to columns, and C++ value types to database types. Here's an example of such a mapping. Again, we use additional pragma words to specify table name, column, and the type which it should map to. Okay, now the interesting part, the most interesting part. So we have our persistent classes and the ODB compiler generated schema for us. If your classes never change, then you're all set. The rest of us, however, have another problem on our hand. And that is what happens when we, for example, add another data member to one of our persistent classes. What happens to our existing databases? Who is going to update the schema and, if necessary, convert the data? Now, the database schema, the schema evolution support is very new in ODB. It's implemented, it's in the repository, but it will only be publicly available in the upcoming version. So I'm quite interested to see what you guys think about the whole setup. Also, the schema evaluation is a very sensitive topic because normally there's production data at stake. If we do something wrong and it's gone, that's a bad thing. So there's always this trust issue. So as a result, we've decided to come up with a set of simple, easy to understand building blocks without any magic that we cannot trust. So trying to do it as simple so that you can have a clear idea of what happens at each step. Schema evaluation can be divided into two subtasks: schema migration and data migration. By schema migration, I mean changes to the database schema, such as adding a new column, while data migration involves converting of the existing data from the old format to the new one. ODB will take care of schema migration and leave the data migration for you. Remember, there's no magic. But as we will see now, there's actually some nice support for data migration that is provided by ODB. But in the end, only you know the semantics of your changes. The first thing that we need to do to enable schema evolution support in ODB is to specify the model version, or more specifically, two versions. The first version is the base model version. It is the earliest version from which we will be able to migrate. The second version is the current model version. Now, the idea of the base model version is, remember you developed for 3 years and went through like hundreds of versions. You don't want to maintain the information about all of them. So sometimes you would move the base version a little bit forward, and then all that old stuff will be automatically dropped. So that's the idea of why we have two versions. Okay, so let's say we forgot to add, or we realize we need a new field in our bug report, say a platform. First thing that we do, we increment the current version and then we add the data member. Once the ODB compiler sees the version pragma, it starts tracking object model changes in a changelog. Now the changelog is an XML file, and why XML? Well, we needed a human-readable and machine-readable file format, which is both easy to parse and merge, easy to diff and merge, as well as analyze and process with third-party tools. So XML sounded like a nice fit. The changelog contains the base model, complete base model at the bottom, and then a sequence of change sets, one for each version. The changelog is maintained completely by the ODB compiler. However, you will treat it as one of your source files, and for example, store it in your source code repository. Now that might seem iffy, but the point here is that you actually need the changelog that was generated or updated on the previous execution of ODB compiler is actually used as an input for the next execution of the ODB compiler. This is what the changelog looks like for our example. So there is the complete base model recreated, and there is the change set for our version number 2, where all we do is add a platform column to our bug table. Once the ODB compiler given the changelog, the ODB compiler can now generate schema migration statements all the way from the base version to the current version. Similar to schema creation, it can either do that as a set of standalone SQL files, or it can be embedded into the generated C++ code. And now that's where it gets interesting. For each migration step that is from one version to the next, ODB generates two migration files, the pre-migration and the post-migration file. The pre-migration file relaxes the schema so that both data that conforms to the old format and to the new one can coexist. During this step, new columns and tables are added while old constraints are dropped. During the post-migration step, tightens the schema back so that only the data conforming to the new format can remain. During this step, old columns and tables are dropped and new constraints are added. Now, who can guess where the data migration fits into this? I think everyone can guess. So that's between pre-schema migration and post-schema migration, when we have access to data, to both old data and we can create it into the new data format. I'm not aware of any other ORM that does something like this, so I am very excited about this stuff. I think it's... Oh. So let's take a look at our example, at the pre and post migration steps for our example. As you would expect, the pre-migration file actually adds the new column. Notice something interesting here. We add the column as null, even though the thing should be not null. This is tightened up in the post-migration step, as you can see. Like, why do we need to initially add a column as null? If the bug table already contains any rows, then adding a non-null column without any default values will fail. By first adding it as null, we give the data migration code a chance to set all this value to some meaningful value, this column to some meaningful value for all the existing bug reports. Let's take a look how we can do that. Here I'm using embedded schema migration to see how everything fits together. First we pre-migrate the schema. Then we set the platform to an unknown value for all the existing bug reports. And then we post-migrate the schema. Now, this example is a bit contrived in that we could have achieved the same result by simply adding a default value for the column. The idea here is to show a more general approach which can be used for more complex data migrations. Now, we may not want to perform each schema and data migration step for all the versions from, that and this and that ourselves. Good news is we don't have to. Instead, we can register data migration steps for versions that require them. Here we use a C++11 Lambda. And then we just do both schema and data migration for all the necessary version steps in a single function call. Okay, any questions about this? No?
Do you also produce the migration as SQL files?
Yes, you can either do it as separate files, set of separate files, or sorry, the question was, do we also produce, can we also get the migration statements as a separate SQL files? And yeah, the answer is yes. Either a separate set of SQL files or embedded into C++ code. Okay, that's pretty much it for the features that I had time to go into detail. Let me also mention a few others briefly. We can use smart pointers, ODB nullable or boost optional to handle null columns. ODB also has the notion of session, which by default is just an object cache. But we can also provide a custom session with application-specific and more advanced functionality. For example, you can implement a session that automatically tracks object changes and then does state flushing for those that have been modified. Then we can use Pragmas to define database indices on one or more data members. The other really cool feature, I think, is virtual data members. The idea here is that you can create columns in the object table without actually having any physical data members in the class. This, for example, is very useful to implement something like a pointer to implementation idiom. Also, this is a Swiss Army knife of mapping existing stuff to the database. Just the other day, someone wanted to map a C++11 tuple, and it wasn't easy because if you know how the tuple is implemented, it's like a recursive base class stuff. So yeah, I could map it with the virtual data members using all this get 0, get 1 as an accessors for the fake members. Let me also, the other thing is ODB is highly customizable. I think you kind of saw it as a theme throughout the talk. We can provide a custom mapping for value types to suitable database types. For example, we can map our own datetime type to a suitable database type. Then we can add support for custom containers, custom smart pointers, custom null wrappers. So if you have your own equivalent to boost optional, you can use that. Then, as I mentioned, we can provide a custom object cache with application-specific functionality. When it comes to Boost and Qt, ODB actually doesn't know anything about them. Well, ODB core, those are implemented using generic mechanism, which you can use to create your own profiles. Then, these days, besides common types like integers and strings, most modern relational databases provide a slew of extended data types. Things like XML, JSON, containers, special types. The list goes on. ODB provides a generic mechanism for mapping these extended types to suitable C++ types. Just to give you an idea of what's possible, I don't know if anyone is familiar with the Postgres HStore extension. Well, essentially, it's a string-based key value store. So you can store a key value in a cell in your table, in a column in your table, just like a single value. So in ODB, we can map this to something as something like standard unordered map. Then you can also specify the database operation callbacks on per class basis. Those will be called whenever before and after a database operation is performed. This, for example, can be useful to implement post-load operations such as computing some transient values. Then you can provide your own connection management strategy such as connection per thread, and by default connections are pooled. We also mentioned quickly what's in store for ODB. One feature that we are asked a lot for is the ability to generate C++ classes from database schema automatically. So that will probably be the next big feature. Then, as I mentioned earlier, for now we only support lazy loading of pointer to objects. But it would be cool to also allow loading some other data members lazily. For example, a blob, if you don't need it very often and it's very big, it can be expensive to load. So there are plans for that. Then what people also ask for, especially in the finance industry, for some reason, is support for bulk operations such as bulk insert in databases like Oracle and SQL Server. So there are plans for that. Then there are additional then we are planning to support additional schema migration steps, such as some databases allow you, for example, to rename a column or a table. So there are plans for that. Then there are some more speculative features that we might support. We've seen some interest in support for the DB2 and Firebird relational databases. Then it seems like might be a good idea to also support a non-relational database such as a MongoDB, for example. The biggest obstacle here is that most of these databases don't really have transaction support, so it's still a big question. Then it sounds natural to extend ODB to allow you to save your objects besides database to also say XML or JSON. So maybe something like this will happen. Then it seems like sharding is something that ORM can handle or maybe at least help with. And that's it from me for today. Thank you all for your attention. I don't know if I think we have a couple of minutes, but yeah.
The profiles you mentioned?
Yes.
How are they built? Are they just text files, or are they required?
Well, a profile is a library, and then the customization mechanism is based on this concept of threads. I don't know if you're familiar. So there's a class, for example, a pointer threads, and then you just specialize it for your pointer and implement a couple of functions, how to get the reference and things like that. So a profile is basically a library that contains a header file with a specialization of a threads, let's say for boost shared pointer.
So it ends up being source file.
Yeah. Well, a profile is basically a bunch of source files packaged in a library.
It's just C++.
Yeah, standard C++, yeah. Okay, I think that's all. No more questions.